How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at 4.4b redox reactions. We're going to take a look at metal activity and spontaneity. So our objectives will be to predict reaction spontaneity based on the activity of metals. Basically, if I mix this with that, is it going to react? That's what we're going to look at. All right, so redox reactions. In redox reactions, atoms are losing electrons, which again is oxidation, and others are gaining them, which we call reduction. Electrons are being transferred. One thing's losing them, the other thing's gaining them. But why? Why is this happening? All right, well, it comes down to differences in activity. So here on the right, you can see I have an activities chart, and you can see potassium on this chart is at the top, so it's the most reactive of the ones we listed, and platinum's at the bottom, so it's the least reactive. So some metals want to be oxidized more than others. I put quotations around want because these things don't actually have any wants or desires or thoughts. They're just atoms. But I like to think of them as like, having wants and needs. And some metals want to be oxidized more than others. For example, if magnesium were to come in contact with copper ion, there would be a reaction. Well, let's take a look. We got magnesium up here, and we have copper down here. So we know metals like to be oxidized. So if we take a look here in this example, copper has a +2 and it's oxidized, but magnesium is not. So if these two things came into contact with each other, magnesium is going to be like, hold up, I'm more active. I want to be oxidized more than you, copper. Something's got to change. Right now, you're the one that's oxidized. I don't like that. So because it's more active, yeah, that's what I said. So it's going to transfer electrons. It's going to be, hey, copper ion, I don't think so. You're taking my electrons, and I'm going to be the one that's oxidized. So here is a time-lapse video 4 times of that happening. Here I got magnesium metal. I'm putting it into a solution that has copper ions, and you can see almost instantly it starts reacting and corroding, and the magnesium's oxidizing, and it's reducing the copper ions that are in solution. You can see it starts to discolor. There's a reaction going on. So what's going on inside my head? Well, maybe I'm not normal, but this is what happens, right? I'm picturing these magnesium atoms. They got these 2 valence electrons, and we got this copper ion that's gotten rid of 2 valence electrons, and they're like people. So magnesium's like, yo, copper, what's up with this? How are you going to walk around all oxidized and stuff when you know that I want to be more than you do? And copper's like, oh, all right, what are you going to do about it? Punk, magnesium, huh? What you going to do? And the magnesium and copper, they go at it. They start fighting. Like, bam, bam, bam. Who's going to be oxidized? Who's going to win the battle? Well, magnesium is because it's more active. So copper ion's like, all right, fine. You can be oxidized. I'll take those electrons. Whatever, man. So magnesium's like, that's right. You're taking these electrons. Well, what happens to the charge then? Well, the copper is going to lose the +2 charge because it gained 2 electrons. And magnesium's going to become +2 because it got rid of those 2 electrons. And the magnesium's like, yeah, that's what I thought. Right, so that's what goes on inside my head. But what if the magnesium ion bumped into a copper atom? So again, we find magnesium, it's higher up, copper is lower. So magnesium wants to be oxidized more, but it already is. All right, so we don't get a reaction because it's fine. This is what goes on in my head. Magnesium shows up, it's like, yo, copper, don't you know I want to be oxidized more than you? And copper's like, yeah, I know, and you are. There you are, oxidized. I'm not over here. Magnesium's like, oh yeah, that's right. I guess we're cool. Copper's like, what an idiot. What was that? Oh, what was what? Huh? What did you say? Right. So no reaction occurs when the thing that's more active is already oxidized. All right. So reactions with acid. Typically, we don't think of hydrogen as a metal, but it can lose electrons just like metals. So it's typically on the chart for the activity of metals because we're usually interested in, like, will it react with acid? So acids give off H+ ion. So here's a reaction. Let's figure out if it's going to react. We got hydrogen +1. We got chlorine -1. Magnesium 0. Here magnesium's +2. Chlorine's -1 still, and hydrogen 0. So we're looking at the starting reaction. We got H+. And we have Mg0. So let's take a look at our activities chart to find these things. I got magnesium. I got hydrogen right here. So which one wants to be oxidized more? Magnesium wants to be oxidized more. So if we take a look in this setup, magnesium isn't oxidized to begin with. So something's going to have to change. We're going to get a reaction. So if you put magnesium in with some acid, you're going to get a reaction where the magnesium is going to lose its electrons, and it's going to give them to the hydrogen. All right, so will a reaction occur? I dare you. Pause it, try to predict whether or not a reaction will occur, and then unpause it. Right, pause it. All right, welcome back. So let's figure this out. We got magnesium, that's 0, and sodium, that's +1. Well, here I found magnesium, and sodium's up here. So which one wants to be oxidized more? The sodium does, and it already is. So you're not going to get a reaction. No RXN reaction. Because the thing that wants to be oxidized more already is. All right, here I got potassium with a 0, zinc with a +2. Let's find those things. I found zinc right here, and potassium up there. All right, well, hold on. Potassium is more oxidized than zinc. It wants the positive charge, and in this setup, it doesn't have it. So we're going to have to get a reaction, so that ends up being the thing oxidized. All right, H, F. So H, we have a plus charge, and AU is neutral, so let's find those things. I got hydrogen, I got gold. So the thing that wants to be oxidized more is hydrogen, and wait a minute, in the acid, it already is oxidized, so you're going to get no reaction. And this is why these metals that are less active than hydrogen are used for like currency and pretty things that are going to last and not corrode, because they're not very reactive. They're not very active. They don't want to be oxidized as much as other metals do. So you can put gold into an acid bath and it's not going to corrode. All right, copper, chloride, Cu+2, and Fe0. So let's find these ones again. Iron and copper. So the thing that wants to be oxidized more is iron, but it's not here. Here it's not oxidized, and it wants to be oxidized. So we're going to get a reaction. Something is going to have to change. So there you go. So what metals won't be corroded by acids? Again, we're looking, acids give off H+, so any of these metals, whether it be copper, silver, gold, or platinum, they're not going to be corroded by acids because they're less active than hydrogen. So summarize. Can you explain why redox reactions occur? Can you predict if a redox reaction will occur, aka be spontaneous, based on the activities of metals? If I gave you a chart, could you figure that out? All right, and here is the video, the rest of the video, of the magnesium being corroded by the copper sulfate.